Okay, and so think about when you started a new job, first day at Walmart, first day at Target, whatever. You didn't know everything. You're like, oh, what the heck is going on here, right? Or just even your first day at ECPI, you're like, what room do I go to? Who do I talk to? How on earth do I use this canvas? Why is my computer not working? You didn't know about, the Authenticator app and everything else, right? Why? It took you a while to adapt, right? To learn how to be a good student. Same idea here with the immune system. So one of the things is this adaptive immune system is going to take about 10 to 14 days to kick in, right? And so during that time, what's keeping us alive? Well, it's the innate immune system, right? It's still fighting off that virus, trying to keep you from dying while the adaptive immune system kicks in. And so what's going to happen is, you need a prior exposure. In order for your body to adapt, it needs a prior exposure. And so once you have a prior exposure, or you're given antibodies, so if you're talking about a prior exposure, antibodies, one of the ways that we get these prior exposures is vaccines. Well, a lot of people don't realize a vaccine is basically a prior exposure. All right, but once you have something like that going on, we're dealing with the adaptive immune system. And so, the adaptive immune system is going to be, by and large, long lasting, more than another. So let's walk through a couple of scenarios. And so, as you can see on this list, you got natural and artificial, active and passive, right? And so what's going to happen is you're going to get questions and you're going to say, hey, look, this is adaptive, natural, passive. This is adaptive, natural, artificial. I'm sorry, adaptive, natural, active. You could say this is adaptive, active, passive. Adaptive, artificial, passive. Adaptive, artificial, active, right? And so, you're going to have a total of 4 combinations here. All right, so let's run through the situations. So we'll start off with active first. So what happens? I throw up on you, and your innate immune system kicks in, but it's not enough, right? You actually do get sick. And so what happens? You have an adaptive, natural, active, right? If your adaptive immune system didn't kick in, you would die, right? Or you'd be sick for the rest of your life. And so what happens is, what's active? Your B cells are very active. They're producing antibodies, right? And so these are proteins that are going to help us fight off the infections. Your T cells are active. They're actually killing the cancers and basically infected cells. So if a cell inside of your body has a virus, has a bacteria, has whatever, has a cancer, these T cells are going to kill it, and it's going to be very specific. Why? Because you don't want to come down with the flu and your T cells destroy your liver. They were active, but they killed the wrong thing. And so this is part of the reason why it's going to take 10 to 14 days for this adaptive immune system to get off the ground. Our body wants to really check to make sure that the B cells and T cells that are turning on are actually fighting the infection that we're sick with. The last thing your body wants is you're dying of the flu, and oh, by the way, your B and T cells are killing your pancreas, liver, or whatever. Or we're spending a lot of energy fighting, let's say we're spending a lot of resources fighting something you don't even have. That's not helpful. Okay, and in the case of your B and T cells actually fighting normal body cells, that's actually harmful. That's autoimmune diseases right there. Okay, next thing we got right here is this adaptive, natural, active immune response is going to be the best immune response in terms of fighting off infections. So let's run into another scenario. So scenario number 2 let's see what you got right here. So, mom gives birth to baby, baby exposed, but does not get sick because mom already had illness. Okay, so what on earth is going on here? So the first thing you're inclined to believe is, oh, innate immune system. And yeah, that baby is going to have an innate immune system, right? So if mom gave birth, the baby was exposed to something mom's never had before. Let's say mom, she's not got the chickenpox shot, she's never had chickenpox, the baby is exposed to chickenpox and doesn't get it. The reason why that baby didn't get sick was the innate immunity. But in this case, what does it say? Mom already had the illness. So the fact that mom got sick and recovered, what type of immunity does mom have? Well, mom has adaptive, natural, active immunity, right? Mom isn't going to get chickenpox again, chickenpox or the flu or whatever this particular disease happens to be, because her B cells are actively producing antibodies. Her T cells are actively killing any cell that gets infected with that virus. All right. So what on earth does that have to do with the baby, though? I mean, we get what's going on with mom, but what's going on with the baby? What does mom's previous illness have to do with the baby not getting sick? Well, what happens is mom passed her antibodies to the baby. And so that's natural, right? That's totally normal. When mom gives birth, she passes the antibodies in her breast milk. So every time she breastfeeds this baby, she's actually protecting this baby against all the infections that she's had in her past. Also, this gets passed through the umbilical cord. That's also going to protect the baby. So is there a difference between these two? Yeah, what happens is the breast milk is going to be going to protect the mucous membranes. And so basically, if you look in your nose, your eyes, your mouth, your whole respiratory system, your whole digestive system, your urinary system, your reproductive system, anything that has that wet kind of feel on the inside of it, that's going to be a mucous membrane. And so breast milk is going to protect against that. The antibodies you got through the umbilical cord is going to do basically the whole body. It's going to protect the whole body against infections. Now, this is a passive immunity. And so why is it passive? Well, your B cells and your T cells, they're passive. They're not doing anything, right? This baby's body and this baby's B cells and T cells are not producing anti-flu antibodies. They're not actively looking for cells that are infected with the flu. All right. And so it's like that thing, you feed them, you give a man a fish, you feed him for a day. You teach a man how to fish and you feed him for life, right? So this adaptive, natural, active immunity, the B cells and T cells know what to do. They can do this for the rest of your life, right? You don't really hear of outbreaks of mumps in the nursing home. You don't hear of outbreaks of measles in the nursing home. Why? Because as a child, they got measles. And so now they have immunity that lasts their entire life, right? But here's the thing. How many times do you hear children coming down with diseases their parents have had? All the time. Why? Because this is a passive immunity. It will pass away, right? It's not going to last very long. And so mom, when she gives her baby these antibodies through the breast milk and the umbilical cord, particularly the umbilical cord, those antibodies will basically give that baby a 9-month lease on life. Why? This baby has 6 to 9 months to get their adaptive immune system up and running so they can create their own natural, active, adaptive immunities to any infection they come in contact with. So that's going to be those two examples right there. All right. Well, now what about artificial? Well, artificial is something you don't find in nature, right? And so artificial is typically going to deal with a needle in your arm. Some sort of medicine ball is going to be involved, right? So artificial, adaptive, and we'll deal with active immunity. So what's happening in this case is a vaccine, right? And so basically what we're going to do is we're going to put something into your body. Your immune system says, what the heck is this? And so your immune system's going to attack it. And it's going to be the same sort of idea as this this adaptive natural active immunity, right? Your B cells are going to kick in, they're going to produce antibodies, your T cells are going to kick in, and they're going to kill the cells that are infected. Now, the big difference is with this artificial immunity, usually what we have is the infection is dead, right? So sometimes we'll use a protein, and that sort of thing. Sometimes we'll use actually a whole cell. So we'll actually take a bunch of bacteria, heat it up, kill it, put that into your arm. Sometimes it's what's called live attenuated. And so what happened is we're actually giving your body a weakened version of the real thing. And so once again, your B cells and T cells are going to become active and help you fight off this infection. Because this infection isn't as bad as actually getting sick with it, the immunity is not going to be as strong. It's a lot better than nothing, but it's definitely nothing like the real thing. And so here's kind of why we do this. If this immunity is not as good as the real thing, then why do we bother? Okay, well, one of the things is you don't really have to get sick or not as sick as if you got the real thing. So, you get the flu, you get over it, no real big deal. So a lot of people actually don't get the flu shot because really what's the point? I don't get it. I'm not really that sick. It's no big issue here. But where vaccines, artificial adaptive immunity really comes into play is what happens if you don't get over it? What happens if you get over it and now you have long-term problems because of it? So, for example, let's say we'll do smallpox. Smallpox is a great example. If you get smallpox, there's a 30% chance you're going to die. So that means out of 100 people that get sick, only 70 people are left. That's not good, right? I don't want to be on that ride. And so one of the things they'll do is they'll actually give you a weakened version of smallpox. And so what's your chance of dying from the smallpox shot? Well, if you vaccinate 100 people pretty much are going to be left. I'm sure if you vaccinate enough people, somebody will die from the shot. Whatever. You take enough medications, you have enough people that take medication, somebody's going to have a bad outcome. But that sure beats the alternative, right? And so we got enough of an immunity kicking in here that it actually protects you from getting the real thing. And if you do get the real thing, you're not starting off at ground zero. Remember how I was talking about with the natural active immunity, natural active adaptive immunity? Why did it take 10 to 14 days? Why? Because your immune system wants to make sure that the B cells and T cells that it's allowing to turn on are actually going to fight the infection and not target normal healthy body tissues. And so for about 10 to 14 days, we're letting this infection kind of rage uncontrolled or barely controlled, because we're relying on our innate immunity that's not able to fully control this infection. One of the huge benefits of this artificial adaptive immunity, even if it doesn't 100% protect you against a disease, is we don't have to wait 10 to 14 days for your immunity to kick in. So adaptive, right? You're learning, you're getting better at things. And so this is true whether you get a vaccine or you get a real infection, is if you need 100 antibodies to kill an infection, after about a year, you have 10. Well, that's going to be very powerful. You're at 10% of the total antibodies that you need to kill a totally out of control infection. And so that's going to be very powerful at preventing infection. It took you 10 to 14 days for immunity to kick in. You get sick a second time, in 3 to 5 days, your immunity kicks in. Let's say that you went from 0 to 100. Well, the second time you get sick, you're going from 10 to unheard of 100,000. So you're absolutely just going to crush this infection the second time around, right? That's the power of active adaptive immunity. Once again, it's not really going to pass away. This right here explains why some people they get sick even after they got vaccinated. Just because why the vaccine doesn't last as long is because you're decreasing your immune response over time. But yeah, it's going to be a very powerful tool right there. The other thing is you're also talking about adaptive immunity. Your antibodies actually work better. So poor antibodies don't work great. These are great antibodies. And so this active adaptive immunity is really going to be very powerful. Okay, let's talk about your adaptive artificial passive immunity. So what's happening here is this is adaptive, right? So we're dealing with antibodies. So antibodies are definitely involved here. But this is passive. This is going to pass away. Somebody passed this person antibodies, right? And so what happens is patient one, right? They were either vaccinated or they got sick and recovered, right? So this person, patient one, has an active adaptive immune response, right? So they're cranking out antibodies. And so it's going to be way harder for them to get sick. All right. Now, what's going to happen is patient number two, they got sick and they got exposed, but they don't want to get sick, right? So their B cells and T cells are not going to do anything. So what's going to happen is we're going to take the antibodies, patient number one, and we're giving them to patient number two, right? And so we took a needle, we put it in your arm, right? We got IV, we're giving you a shot, IM, whatever, right? Or sub-Q, depending on the route. Anyways, typically IV, IG. So we're giving these the antibodies through a shot. So this is artificial adaptive passive immunity, right? Unfortunately, this doesn't last as long as when mom passes her antibodies to the baby. And so this is only going to last, if you're lucky, maybe a couple of months, right? Usually just a couple of weeks. Why? Because their B cells and T cells are not active. And these antibodies are constantly breaking down and being used up as it helps our body fight off this infection. So that's what you got there. The other thing that you want to know about your about your adaptive immune response is once again the antibodies. So IgM is the first antibody that's made when you get an infection or a vaccine. And so this is short-lived. This doesn't stay in the body very long. This is also general purpose. So when you get sick, your body doesn't really know what it's doing. And so it needs to be able to cover no matter what goes through that door, right? And so as things go along, it becomes obvious to the body kind of what type of antibody we need. IgG, basically this is the next couple of antibodies are going to be long-lived. And so this is long-term immunity. All right. And this goes into the body tissues, and this can cross the placenta. So when we talked about mom giving birth, this is what she gave to her baby through the placenta. And so it's going to pretty much protect all the tissues of the body. All right. So IgA, this is going to be your mucous membranes. So one of the downsides of IgG, it doesn't do so good in the mucous membrane. So once again, the eyes, the respiratory system, the urinary system, the reproductive system, the digestive system doesn't do so good here. And so IgA does pretty good here. And so when mom breastfeeds her baby, this is what she's giving that baby. And so basically it's going to stop the bacteria from being able to bind to that baby's gut and beat up the baby or make them sick. But it's also going to educate the baby's immune system. Hey, you see this guy, this bug over here? He's a bad dude. You need to produce antibodies against him. So breastfeeding produces a lot of benefits even after the baby finishes breastfeeding. All right. IgE. All right. I'm going to misspell this next word just to help it stick. This is going to be involved in allergic reactions. I know allergic is really spelled with A, but hopefully the misspelling, the E will help you remember. That's going to be IgE. But yeah, this is involved in allergic reaction. It also helps us fight off parasites. And so one of the things that we're thinking, the reason why we're seeing so many parasites in Western civilization is our eosinophils. Like, man, it's been a long time since I've seen a parasite. Oh, look, there's one. And it'll actually attack totally harmless things. Now, there's some other evidence that something that we're putting in our diet is actually causing these cells to go crazy, and we're producing IgE antibodies against infections that are against things that aren't really infections. Okay, so the next one that we have is IgD, and basically we don't know. We really don't know what these things do, but we do know it is in the blood. All right, so that's what we got there. And yeah, when we're talking about active and passive immunity, these are the antibodies primarily, not so much IgD, but these are primarily the antibodies that are made. One of the things that can help, that helps me remember the names is G made, right? So IgG, IgM, IgA, IgD, and IgE. Okay. So next thing we got is natural killer versus T cell roles. And so this is going to have a little bit of an overlap here. And so let me explain that real fast. All right. So I'll kind of start off with killer T cells. And so the killer T cells, they're part of the adaptive immunity. All right, and so remember what I talked about, the adaptive immunity, it's going to be specific, right? The last thing the body wants is a T cell going through and killing off your pancreas. a T cell going through, killing off your heart just because you happen to come down with the flu. Not good, right? And so our body has to go through all these checks. Okay, are we really sick? Yes. Are we sick with this particular bug? Yes. Does this T cell match that particular bug? Yes. Okay, we're going to let that T cell kick in. So it's going to take a while for those T cells to kick in. And so the T cells, they kill cancer/infected cells. And here's the word, specifically, right? And so what do I mean by that? So I'll just add a bunch of numbers here real fast. So, all right, so we got T cell 1. So T cell 1 only kills cells that are infected with chickenpox. You can be dying of the flu, and this T cell's not going to lift a finger, right? Why? It only deals with chickenpox. All right, T cell number 2, let's say that this T cell only kills, let's say, so myelin origin brain cancer. And so let's say you're dying of brain cancer that comes from the astrocytes. Well, this T cell is not going to lift a finger. Even though it's a T cell that kills a cancer cell, a type of cancer cell, because this can't, because your cancer cell is an astrocyte origin brain cancer, it's not going to touch it. Why? Because this only fights off brain cancer that comes from the myelin cells, right? So the oligodendrocytes. So you see what I'm saying? They're going to be highly specific. And so the good news is, because we have so many of these, you know, it adds up. So, so it adds up over time. And so we got thousands of different types of T cells. I just made up a couple of numbers. You know, some people ask, well, why do I get the flu each year? Because the flu isn't just one bug. So you might have a T cell that's specific for flu 147. But if you have flu 148, you're out of luck. This T cell's not going to help you, right? And so now we have to have this other T cell activate, and then this T cell activate. And so that's why people constantly get the flu, even though they've had it before. All right. Now, that's your T cells. And each of these is going to take about 10 to 14 days after the exposure to turn on. All right. Now, let's talk about your natural killer cells. So your natural killer cells are non-specific. All right. They're part of the innate immune system. And so what I'm going to do is I'm actually going to talk a little bit about how they work, and this will actually help you better understand. This will help you better understand, you know, why they are non-specific. And so what you got right here is, we'll say this is a normal cell. And so what's going to happen is it's going to have its receptors. And so I'll just do two different shapes, just for the sake of simplicity here. And so what's going to happen is these cells are constantly working, they're constantly doing things, and so they're constantly showing the immune system, hey, what have I done today, right? For those of you that have kids in school, think about it. Your kid goes to school and, you know, they send them home with a folder that shows their grades and everything they did. This is what they did in math. This is what they did in science. And so if your mom or your dad, you get this folder down back, you can say, whoa, wait a minute here. What the heck is this thing? Man, you did really bad at that, right? And so you're gonna activate, you know, and you're gonna help that child adapt to that subject. Well, it's the same thing here. If this cell becomes, you know, this cell's constantly telling the body what they're doing, And so the immune system going to come through, oh, yep, that's normal. Yep, this thing over here is normal. But if they see something goofy, the adaptive immune system is going to come in and then it will kill the cell that's affected, right? So if you're a virus or a cancer, that's not a very good plan for you, right? Last thing you want to do is to be killed. So you don't want to tell the body what you're up to. And so what are you going to do? Well, for those of you that have kids, if they do really bad in school, what happens to that folder? Sometimes it just magically disappears, right? Oh, Susie, where's your folder at? Oh, I left it at school. It was an accident, right? No, it wasn't an accident. They don't want you to know they did really bad at math or science or whatever, right? And so a lot of cancer cells or cells that are infected with virus, or in some rare instances, you can have bacteria or whatever that live inside the cell. They magically lose that folder, right? So the cancer cell or the virus will down-regulate these receptors. That way the immune system doesn't know what's going on. Well, the natural killer cell says, look, I don't know what's going on with you, but I'm just going to kill you, right? And so the power of that natural killer cell is really quite crazy, quite astounding. And so, going back to our T cells, right, we have to have thousands and thousands of different T cells because each only kill one type of infection, each only kill one type of cancer, and it's extremely specific, right? But these natural killer cells, you can have a natural killer cell that kills a virus that's infected with the flu, kills a virus that's infected with chickenpox, kills a virus, kills a cell that has cancer, the same T cell, right? And so it can just kill several cells, all of which have different cancers, all of which have different viruses. Why? Because it's not specific. It doesn't know what type of cancer it has. It doesn't know what type of virus it has. The only thing it knows is that they're missing the normal receptors that are telling them, hey, what's going on? And so that's the power there. And that's going to be the difference between those natural T cells, those natural killer cells and those T cells. All right, well, hopefully that helps. If you have any more questions, definitely let me know. All right.